Today we're going to be learning about logarithm graphs, and the image right in front of you here is really just to show you that it doesn't really matter what the base is. Well, we usually look at doing a log graph base e. If it's base 2, base 10, base any number really, it shares a lot of similarities. One is that looking at this, all the graphs cross the x-axis at 1, 0. And this is because log of anything, 1 is equal to 0. So we might determine that by saying log base a of 1 equals 0. The vertical asymptote is at x equals 0 because anything inside the log has to be greater than 0. We might say here that the domain is real positive and 0. We also want to make sure of that. The range is real and they're all increasing functions. Generally speaking, if the value of a, the base of the log, is small, then the graph might be more steep and it might more rapidly rise. If the base is bigger, like 10, then you might not see such a rapid rise. However, you will notice that 10, if we highlight it here, actually approaches the asymptote a little bit faster than something like log base 2. If we imagine the graph of y equals a log e nx, it's really important to recognize a few things about the shape. For the basic graph where a is positive and n is positive, so let's just suggest here that a is greater than 0 and n is greater than 0, we can expect an asymptote at x equals 0 and a shape that looks something like that. In the instance that a was negative and n was positive, we might call this a reflection about the x-axis. Still going to have the asymptote at x equals 0, but obviously we're going to flip about the x-axis. We might also consider the case where n is less than 0. Same thing, but if we're reflecting about the y-axis, the shape is going to look something like that. If we're now sketching the graph of y equals 2 log e x plus 5 minus 3, we need to consider what the question's asking us. So, very simply, we're asked to sketch the graph, and we're also asked to state the implied domain. The graph in question is 2 log e x plus 5 minus 3. When we're looking at this originally, we might want to think about what we know first. And we can see here that 2 is positive, there is no coefficient of x, and so the general shape of the graph might look something like this. We can also have a think about where the asymptote will be. Looking at what's inside the logarithm function, we might consider down here x plus 5 ought to be greater than 0. Therefore, x must be greater than negative 5, and we could imagine an x asymptote at negative 5. So we can start by drawing that in. And I'm really after a dotted line here, so we'll just get rid of that ruler, and we'll get a rubber here. Close enough. Really important that we label our x asymptote, so we'll say here x equals negative 5. Just like any graph, we want to determine if there would be y-intercepts or x-intercepts, and looking at the shape of this graph, as we're drawing it here, we can see there'll be both. I'm drawing arrowheads on the end to indicate that this is a continuous function. Just like any graph, if we're finding the y-intercept, we're going to let x equal 0. So assuming here that y equals 2 log e x plus 5 minus 3, we might be thinking to ourselves that we're now after the y-intercept, and so we'd let x equal 0. At first this might seem somewhat difficult, until we remember that log e5 is just a number. And so this is all we have to do. The intercept is literally 0 and 2 log e5 minus 3. So we can label that now. X-intercept can be a little bit more involved. Here we're saying that 2 log e of the x-intercept plus 5 minus 3 equals 0. So remember what we're finding here. What we've actually done is said that the x-intercept is where y equals 0. If I transpose this by adding 3 to both sides, and then dividing both sides by 2, we end up with the case that log e x plus 5 is equal to plus 3 divided by 2. If I now base e to both sides, we find that x plus 5, remembering here that e to the log e will cancel, is equal to e to the power of 3 over 2. Last step being that my x-intercept is equal to e to the power of 3 over 2 minus 5. And all I've done there is subtract 5 from both sides. Again, while this may look a little bit complicated, we remember that this is just a number that doesn't need to be simplified. Labelling my x-intercept here, we've got e to the 3 over 2 minus 5 and 0. Last step here, if I just make this a little bit clearer that that's a negative 5, the last step here is to look at labelling the domain and the equation itself. Now, looking at this, I'm just going to bring up my colour for contextualising. The asymptote at x equals negative 5, and we worked out from here that the domain is that x is greater than negative 5, but we know that it's not inclusive. So we might list the domain as domain equals not inclusive negative 5 to infinity. It also may not be entirely obvious that the range in this case is reals. And although this curve does look like it peters out kind of about here, it will continue going on to infinity, and that's important to note. Last step might also be to label the graph. So we'll put in here, oops, my bad. If we just get our pen back, y equals 2 log e x plus 5 minus 3. Okay, so if we have a look at what we're being asked to do here, similar question in that we have to sketch the graph and also state the implied domain. What's a little bit different about this is that there's both a reflection in the x-axis and also a reflection in the y-axis. This might be a little bit more obvious if we rewrite the question as y equals negative 3 log e negative x plus 1 plus 2. We can see here that the asymptote is wherever negative x plus 1 needing to be greater than 0 implies negative x is greater than negative 1, which is to say x is less than 1. So I'll get out my ruler and rule the asymptote. And here we'd label that as x equals 1. We know that the graph is going to be to the left. We know from being reflected in the x and the y axes that it's going to look something like this in shape. It's important though that we think about where the x and y intercepts are going to be. So if we start with finding the y-intercept, we do this by allowing x to equal 0. Y equals 2 minus 3 log e 1 take away 0. Write that in there. And remember, we're finding the y-intercept. Now, the thing about log of 1 is that e to the power of anything that equals 1 must have been e to the power of 0. And so we find that the y-intercept here is 2 take away 0, simply 0, 2. We can label that now. To find the x-intercept, we let y equal 0. So in this case we might say 2 minus 3 times the natural log of 1 minus x equals 0. We can solve this here by saying log of 1 minus x. Now if I subtracted 2 from both sides and I divided by negative 3, we end up with 2/3. We can rewrite this as 1 minus x equals e to the power of 2/3 if we base e both sides. If I subtract 1 and then multiply by a negative, I find my final answer that x is equal to negative e to the 2/3 plus 1. And we know this to be a negative number. We can label it on our graph as 1 minus e to the 2/3, and we know that our graph shape needs to pass through these 2 points. Hopefully your graph will be a little bit more of a solid line than mine is. Last step is to put things in context, label anything that the question asked us to. In this case we need to state the implied domain. We can see here that x is to the left of 1. We can see that because this is where our asymptote is. So here we'd say the domain is that x is an element of negative infinity to a disclusive 1. The range is also going to be reals, and that's usually the case. And the equation y equals 2 minus 3 log e 1 minus x. Now we come across some slightly different questions, which ask us to work backwards, so to speak. We're being asked to find the equation of a function. So whenever I'm looking at a big worded question like this, I try and think, what's the question here? And if I look for my directive word to find, we're asked to find the equation of a function. In order to do this, I'm being told that f of x has a standard equation, a e to the x plus b. I know that I need to find things correct to 2 decimal places. And I can also see that I'm being asked to explicitly state the values of a and b. Use that to find the equation of the graph. So we'll start with what we have, which is the fact that f of x is of the form a e to the x plus b, I know that f of 0 is equal to 2. And I know that from here. I also know that f of negative 2.44 is equal to 0, which we can also read from the graph. And given that I have to find this correct to 2 decimal places, this is just a technology question where we can go menu, whoops, get out my pencil. But if we went menu, algebra, solve, system of equations, we could input this information. So the first equation, where we might substitute the fact that f of 0 equals 2, is to say that a e to the x plus b might be equal to y, in this case f of x, where we just substitute in 0 for x and 2 for y. We've said that e to the 0 is 1, and so we might conclude that a plus b equals 2. We also know that whenever I sub in negative 2.44, we'll get 0. So the second equation we can solve is a e to the negative 2.44 plus b equals 0. This can easily be solved in your calculator. When I do solve this in the calculator, I find that a is equal to 2.19, correct to 2 decimal places, and b is equal to negative 0.19, excuse me. It's really important when putting this into context that the question did ask us to hence find the equation. So I've demonstrated that I found a and b, and I know that the equation will now be f of x equals 2.19 e to the x minus 0.19. Looking at our next question, it asks us to find the values of a, lowercase p, and capital B, and hence find the equation. So it's really important that this is the way I go about finding the equation. It tells me that my equation itself is of this general form a log e x plus b plus b. One way in which this differs, if I think about what we have here, we can see that we've got an asymptote at negative 1, the point 0.5, and the point 2.0. So right away, I can see that b must be equal to 1. Now, if I imagine x plus b having to be greater than 0, and I know that x must be greater than negative b, and I knew that from my equation here x is already greater than negative 1, I can see here that b equals positive 1. Another way to remember this is that whenever we're looking on the inside of that logarithm, if we're ever looking at trying to describe translations along the x-axis, we usually do the opposite of what we see. So right away, I can start with the fact that lowercase b is equal to positive 1. So I now have the fact that y, our graph, is equal to a log e x plus 1 plus a capital B. I also know that whenever x equals 0, the whole graph equals 5. So if I sub in x equals 0 here, I'll get y equals a log e 0 plus 1 plus b. Remembering that log e of 1 is equal to 0, that would mean that a times 0, so that also cancels, is equal to 5, which in this case tells us that b equals 5. The last thing that we can substitute is the fact that when x equals 2, y is equal to 0. So I now know that y is equal to a log e x plus 1 plus 5. And I know that if I'm substituting in the 2 for x, so now this would mean that we have 3 on the inside of the brackets, plus 5, we know that that ought to be equal to 0. Now one way that we may wish to get rid of this a is to resolve it by bringing it to the power of 3. But we don't think we're going to try that just yet. If I let a log e3 now equal -5, and I divide both sides by log e3, then I can see that a is equal to a number which is -5 over the natural log of 3. As complicated as this seems, it is just a number. It is just a constant. And so now we have all the information we need. Just to say y equals -5 over the natural log of 3 times log e x plus 1 plus 5. And reality is, if I had a calculator here, I might use an approximate value for -5 over log e3. Our last skill here is quite a simple one. It's just to solve a standard equation. We can see that from the directive word to solve. Now, looking at the equation 3, let's just get my pen back out. 3 to the 2x minus 1 equals 28. The first thing that I might do is think I have a base 3 here, so it might be worth me logging 3 both sides to get rid of it. So if I do log 3 and I put in here log 3, then I'll know I can resolve 2x minus 1, and log 3 of 3 is 1, so I get 2x minus 1 equals the number log 3, 28. If I add 1 to both sides, then 2x equals log 3, 28 plus 1. And if I multiply both sides by a half, I get x equals, I'll just bring up another colour here, 1/2 times log 3, 28, and of course I have to times that 1 by a half as well. Complicated though this may seem, it is just a number. It hasn't asked me to solve correct to any decimal places, so I would just leave it as is.